Hello everyone, welcome back to ptet.chemistry channel. So this is a continuation of topic 3, this topical MCQ. This is on chemical structure and bonding. So this is a 5-question MCQ series from 11 to 15. So this question is asking you which ion is most polarizing. So you might not have heard of this before, but there was a chemist, he's called Fulgen. So there's a set of rules. It's just basically a general rules, but it basically tells you that, it depends on two things. When you have cations and when you have anions. So cations become more polarizing and anions become more polarizable. So the polarizing is doing the action on the anion, which is polarizable, okay? The cations polarize the anions, all right? So in terms of the factors, we talk about the charge of the cations as well as the size of the cations. If we want it to be more polarizing cations, we want charge to be high, we want size to be small. This is to do with charge over size or volume. And you will have learned this if you have done your A2 chemistry, which is to do with charge density. In fact, that is how you justify how strong ionic bonds are as well, right? In terms of the charge of the cation and the size of the cation as well. And this is the same thing for the anion, charge and size. So they become more polarizable when you have a bigger size, okay? And when your charge is, let me think, I want to get this right. Small cation, big anions. Yep, when your charge is high and when your size is big as well, alright? So, but definitely the size is big. I kind of forgot what this is exactly for it to be more polarizable anion, but definitely you want a bigger size anions. So like iodide would be more polarizable than bromide and chloride. Anyway, this is important here. We are concerned about the cations. So in terms of these cations, so Na plus, Mg2 plus, Al3 plus are what we call the period 3 chemistry. So barium 2 plus is more shells. So the size is bigger. When the size is really big, it's not very polarizing. So I can cross out B. But in terms of ionic, or in terms of radii, if I just say atomic radii, we know the atomic radii from sodium all the way to chlorine decreases. And then we also know that the cations, so the Na plus will be there, the Mg2 plus will be there, and the Al3 plus will be there. They decreases in that order. So Al3 plus is the smallest, and in fact you can find it from the data booklet as well. Although you should really by right know the trend that the ionic radii also increases. Smallest cation, highest charge cation, charge density is the highest, therefore it's most polarizing. Okay, I think I've spent enough time explaining Fulgen's rule there. Next bit is asking on which molecule is planar. So planar means they are flat in the screen of this paper or in this screen that you are looking at. It's to do with shape of molecule. So I hope you know NF3 is going to look like, think about your ammonia molecule. So each fluorine will form single bond to the nitrogen, like hydrogen, but you will have lone pair on the fluorine. So there's actually one lone pair on the nitrogen because, well, nitrogen is in group 15. It's used 1, 2, 3 of its 5 outer shell electron for bonding. It still has one lone pair. It's got 3 bond pair. And this is not planar. It's trigonal pyramidal, 107 degree, right? So it's not planar. It's trigonal pyramidal. So not A. C2Cl4. I hope you can think about C2H4, which is a case study even from O-level. And you can tell by drawing, I'm drawing the 3-dimensional diagram where I'm tilted it sideways. But sometimes you will have seen it being drawn on paper, just like that. So that is flat in the screen of the paper because each of the carbon is 3 bond pair and 0 lone pair. Because 1, 2, 3, you count the sigma bond for the bond pair. And then the one electron left on the carbon, which are on unhybridized orbital, they can overlap sideways to give you the pi bond. All right. So that is carbon sp2. This is trigonal planar, 120 degree. Okay, so B must be the answer. When you look at C3H6 and C3H8, okay, so you might think that this is alkene. You might think that they follow the same thing, but when you look at the alkene, you will have realized that there's only one double bond. So there is a C3H6. So this is 120 degree. This is 120 degree, but this is 109 degree because there's a carbon sp3. These two are carbon sp2. We talk about carbon sp2 being trigonal planar, so it's flat here, but here is tetrahedral because you got 1, 2, 3, 4 bond pair and 0 lone pair. You got 109 or 109.5. That's your tetrahedral there. So that is not flat. Whereas it's asking for which molecule is planar, the whole molecule. All right. I'm not going to draw the C3H8, but you can imagine that this is an alkane. And you don't have a carbon-carbon double bond, so you get all carbon sp3. So all the carbon here will be tetrahedral, 109 degree. They wouldn't be planar. So next is asking you on gecko. So it's kind of like a small lizard, yeah. So it can stick itself onto the glass surface, which you can imagine, you know, it's quite a hard thing for us to do. We're not Spider-Man or Gecko Man or whatever. So what's the attraction between the gecko and the glass surface? It's not going to be ionic bond. It's just going to be straight van der Waals forces because of these tiny pads they have. So each of them interact with the glass surface via van der Waals forces. So they can move easily by forming, breaking, you know, over time, yeah? Okay, so very straightforward factual question there. Next bit is on valence shell electron pair repulsion, which is to do with bond shape and angles. So what do we know? So they want pH3. Well, you can think about NH3. When you have group 15, phosphorus is just below nitrogen. So both of them have 5 outer shell electron. So pH3 is going to look like that in 3 dimensions. You count the sigma bond, which is 1, 2, and 3 single bond. So 3 sigma bond give you 3 bond pair. 5 outer shell electrons, 1, 2, 3 for bonding. Still has 2 electrons, not used for bonding. That is called 1 lone pair or 1 non-bonding pair of electrons. That will give you trigonal pyramidal. Of course, you need to write down the full thing, yeah? Trigonal pyramidal, just 107 degree or 107.5. However, what have we got here? It cannot be 120 because it's not planar. It cannot be 90 because it's not square planar. So which one would you choose then, like between 104 and 109? Typically 109 we associate that with being tetrahedral. But because we have this, we would think about bond pair, lone pair, repel more than bond pair, bond pair. So it's not the same as 4 bond pair, which will give you 109 degree. So that is 4 bond pair, 0 lone pair. Your 4 bond pair repel equally. So they were not going to repel equally because of valence shell electron pair repulsion. You have a lone pair. The best option here will have to be this. Even though we associate this usually with 2 bond pair and 2 lone pair, it must be that the case where the bond pair, lone pair repel even more, giving you a slightly even reduced bond angle. Alright? I mean, that's the best option I can think of, yeah? Taking into account valence shell electron pair repulsion. Next bit is basically just showing you the lattice structure of 2 solids, X and Y. So these dots, bolded and non-bolded, they represent particles of different elements, alright? Different elements mean cannot be metals. Okay? So you can cross out metallic because metals are elements, and element is only one type of particle or one type of atom, so one type of a subatomic thing, yeah? So it cannot be metallic there. Could it be covalent or ionic? When you have a giant covalent network, you're not going to look something like this. This is how the structure of NaCl actually looks like, where each Na plus is surrounded by 6 Cl minus, and each Cl minus is surrounded by 6 Na plus. There's one more up there. It continues up, left, right, whatever, up, down, left, right. Okay, this is the structure of graphite, where you get that layered structure. Okay, and they can slide over each other layer very easily. That's why graphite is used as a lubricant, right? So that's very clearly a covalent and an ionic lattice structure there, just based on your case study of sodium chloride and graphite from your A-level structure and bonding. Okay, so this is it on this 5-question series from 11 to 15 on structure and bonding. If you like these tutorial videos, please subscribe to the channel and share them widely with your friends, your group chats, with your classmates and your teachers and your relatives. And I'll see you in the next video. Thank you for watching.